In this video, I will describe a decentralized shape formation algorithm for Kilobots. Before looking at the algorithm, let's first look at two basic features of a Kilobot: motion and communication. For motion, each Kilobot has three legs, one at the front and two at the back. When a Kilobot is instructed to move left, it rotates counterclockwise around its rear left leg. To move right, it rotates clockwise around its rear right leg. For communication, Kilobots exchange messages wirelessly. The strength of the received signal is also used to estimate the distance between two Kilobots. To make this clearer, let's discuss a simple star-planet algorithm for Kilobots. In this setup, the center Kilobot plays the role of a star and constantly broadcasts a dummy message. Another Kilobot plays the role of a planet. This Kilobot moves around the star in a circular orbit of unit radius in a clockwise direction. Here's how the star-planet system works. At each step, the planet receives the star's message and estimates its distance based on signal's strength. If the distance is greater than 1, the planet moves right to decrease its distance from the star. Otherwise, it moves left to increase its distance. Repeating this process makes the planet orbit around the star in a circle of unit radius. This orbiting is the foundation of the shape formation algorithm. Orbiting is used by a Kilobot to reach a desired location using the help of other Kilobots. The only difference is that instead of orbiting a single star, a Kilobot must maintain at least one unit of distance from multiple stars at the same time. Let's discuss the shape formation algorithm. To understand this, let's define two separate roles for a Kilobot. One role is to act as a guide, and the other is to act as a builder. Guides are stationary robots that have already occupied a position. These robots constantly broadcast their position to help others with navigation. Once a builder finds a suitable vacant position, it settles down and turns itself into a guide. At the beginning, three guide Kilobots are placed in an L-shaped arrangement. They are labeled as 1, 2, and 3. Kilobot 1 is exactly 1 unit from both 2 and 3, while the distance between Kilobots 2 and 3 is root 2, which is about 1.41 units. To specify the desired shape, each Kilobot stores a two-dimensional shape matrix. This matrix lists the Kilobot number, its two desired neighbors, and the distance it must maintain from them. For example, let's build a rectangle with a width of 2 units and a height of 1 unit. The shape matrix defines the positions of the 4th, 5th, and the 6th Kilobot. According to it, Kilobot 4 must be 1 unit from both Kilobots 2 and 3. Kilobot 5 must be at 1 unit distance from Kilobot 2 and about 1.41 units from Kilobot 4. Finally, Kilobot 6 must be 1 unit away from both Kilobots 4 and Kilobot 5. Here's how the process unfolds. When the first builder arrives near the three guides, it doesn't know which position 4, 5, or 6 is vacant. It assumes that the position 4 is vacant and begins orbiting clockwise. Once it reaches that location, it settles down and becomes a guide. The second builder also assumes that position 4 is vacant and starts orbiting. But as soon as it comes within the communication range of the Kilobot 4, it realizes that the spot is occupied. So, it assumes that the next position 5 is vacant. When it orbits to position 5 and finds it vacant, it settles there as a guide. The third builder also repeats the same process. Initially, it assumes that position 4 is vacant, but after detecting that position 4 is occupied, it starts moving towards position 5. But before reaching position 5, this new builder robot learns that the position 5 is also taken. So, it moves towards the next position, that is 6. When it reaches the final vacant spot, it also becomes a guide robot. This completes the decentralized rectangle formation. Now, let's look at a demo on real Kilobots. Note that in practice, instead of requiring perfect accuracy in meeting distance constraints, we allow a small tolerance called an epsilon margin. A builder is considered to have reached its position once it comes within the epsilon margin of the exact location. This localization method is simple, but it has a drawback. The error in position from one builder carries over to the next. This causes the error to accumulate as the shape grows. For small shapes, This naive localization approach isn't a problem, but for larger shapes, we require a more precise approach. That's where optimization-based localization comes in. In this method, at each step, a builder estimates its absolute position in the XY coordinate system using the known positions of other guides. By working with global positions instead of relative distances, the algorithm greatly reduces the error that would otherwise propagate during the shape formation process.